All right, today we're diving deep. We're going right into the engine room of some of the most sophisticated ships out there to really get a handle on the one system that makes everything else possible: electrical power. So think about this for a second. How does a colossal 20,000-ton vessel just stay put in the middle of a brutal storm? We're talking about a massive drill ship or a construction vessel holding its position perfectly, sometimes for weeks, fighting against insane wind, waves, and current. The answer goes way beyond just thrusters and propellers.
It all comes down to its own self-contained, islanded power grid, a power station that has to be way more reliable and tough than pretty much anything you'd find on land. This is where the real magic happens, and, let's be honest, where the real engineering challenge begins.
So here's our game plan for today. We're going to start with the beating heart of the ship, then get into the nitty-gritty physics of power. After that, we'll see how these generators pull off their incredible parallel balancing act, cover what happens when things inevitably go wrong, and then we'll wrap up with a supercritical pre-op checklist. Let's get into it.
Okay, first up, the big picture. What are we actually talking about when we say a ship has its own power station?
The power station concept basically means you're not just relying on one big engine driving one propeller. Oh no. Instead, you've got multiple diesel engines, and each one is driving its own generator. These are all linked up in parallel to a common grid, what we call the switchboard. And from that central hub, power gets sent out to everywhere it's needed. The main thrusters holding the ship in place, the hotel load keeping the lights on and the crew comfortable, even the massive drilling equipment. It's a seriously flexible setup.
But all that flexibility comes with a trade-off. This kind of system is incredibly complex and, pretty expensive. And you're constantly playing this balancing act. You need enough spinning reserve, that's extra generators running just in case, to be safe. But if you run them when you don't need to, you're just burning fuel and wasting money.
All right, let's zoom in a bit on the fundamentals. How do we actually turn diesel fuel into the controlled electrical force that can move a whole ship? At its absolute core, it all boils down to a pretty simple physics principle. The diesel engine gives you rotation, right? Mechanical energy. The generator takes that rotation and uses it to spin conductors through a magnetic field, and that induces a voltage. That's really it. That's the force that drives everything. But the kind of power we create, well, that's where things get really interesting. Okay, you have got to love the classic beer analogy for power. So the active power, measured in kilowatts, that's the beer itself. This is the good stuff, the useful power that actually does the work, turning propellers, running pumps. This is what's burning your fuel. But to get that beer, you also need the foam. That's the reactive power. This power in kilovars is absolutely essential for creating the magnetic fields in all your motors. It doesn't actually burn fuel, but, and this is critical, it generates a ton of heat in the generator windings. The apparent power is just the whole glass, the total capacity your system has to handle. So what's the big takeaway? Too much foam, too much reactive power, and your generators will start to overheat, even if they aren't doing much useful work. It's a hidden threat that every single engineer has to keep an eye on.
All right, so you've got multiple generators ready to go. How in the world do you connect these massive, powerful machines to the same grid so they can work together without causing a complete electrical meltdown? Well, that's where synchronization comes in.
This is a really delicate four-step dance where timing is absolutely everything. First, you spin the new generator up to speed. Then, the automatic synchronizer does its thing, making tiny adjustments to perfectly match its voltage, frequency, and phase with the live grid. It's kind of like merging onto a highway at the exact same speed as traffic. Once they're perfectly aligned, you close the breaker, connecting it while it's running just a tiny bit faster so it immediately starts to push power out. Finally, its governor and its automatic voltage regulator, or AVR, take over, balancing the load to make sure it's taking its fair share of both the beer and the foam. As the official guidance puts it, once they're connected, these massive machines are totally locked together, spinning in perfect electrical harmony. It really is a remarkable feat of control engineering that happens every single day on thousands of ships around the world. But what happens when that harmony is broken? Because a fault in a system this complex is never a matter of if, it's always a matter of when. And the consequences can be catastrophic if you're not ready for it.
Now, it's really important to get that there are different kinds of failures. An overload, well, that's kind of a brute force problem. You're just asking for more power than the machine can physically give you. But a control system fault, that is so much more dangerous. Imagine its governor fails and goes to full fuel, or its AVR fails and goes to full excitation. You've just created a rogue actor.
This one haywire generator starts fighting the rest of the system, and it forces the healthy generators to absorb all that chaos until they get pushed past their limits and trip offline, one by one, leading to a total vessel blackout.
And this is exactly where modern systems use what's called Advanced Generator Protection, or AGP. It's a much smarter defense. Instead of just seeing an overload, it actually monitors behavior. So look at this diagram. You see the healthy generator, G1, just doing its thing, operating inside its normal window. But now look at G2. Its governor has failed, it's gone rogue, and it's shooting way outside the normal operating lines. AGP sees this abnormal behavior instantly. It doesn't just see a problem, it sees which generator is the problem, and it trips it before it can drag the rest of the system down with it. It isolates the fault right at the source.
So, all this brings us to the final, and I would argue, the most important part of this briefing, your role in all this. A fault-tolerant system is only as good as the protective functions that are actually verified and active.
You should think of this as your mental checklist before you start any critical operation. Let's just touch on a couple of the really big ones. First, reverse power. Is it active? Because without it, a failing engine could actually get motored by the grid, turning your power source into a huge, dangerous mechanical load. Not good. Next, field failure protection. If a generator loses excitation, it stops making its own magnetic field and starts sucking reactive power, all that foam, from the rest of the grid, which can destabilize the whole system. Is that protection ready to go? Verifying these functions isn't just a routine task. It's what's standing between you and a blackout.
And that leaves us with one final thought to chew on. It's a question that every single marine engineer is going to have to face sooner or later, as their most important tool slowly shifts from being a wrench to being a keyboard. Thanks for joining us.